Calculating capacitors in alternating current. What we're going to be looking at in this presentation is how we calculate the value of reactance when we're dealing with capacitors that are connected into an alternating current circuit rather than a direct current. So let's start with a bit of an animation simulation to see what's going to happen. So the first thing we have here is a capacitor. It's connected into a circuit, and we've got a switch here and a DC and an AC source. So first I'm going to put the DC source in just so we can remember how it's going to function in a typical DC circuit. I've got no resistor in here, no resistor anywhere. And so we know that based on that, the amount of inrush current will be quite significant because there is no resistor in that circuit. And the amount of time it's going to take for the capacitor to charge up is going to be extremely low. So let's see what happens. Wow. So it pretty much instantly charged up, and now it's just hanging out. It is fully charged. There's nothing that's happening with it, and it is not going to cause any more current to flow until I connect it to something else and discharge it. So I'm going to open the switch. Let's remove our source. And we're just going to discharge the capacitor. And this time I'm going to put an AC source in there. The AC source is alternating current, and it's the same voltage as the DC source, same voltage. So now I'm going to close the switch. Are we going to have the same scenario where it's going to be like a dead short? There's going to be instant current flowing back and forth and cause a lot of heating or not? Let's see. Well, initially when I hooked it up, it appeared that there was a bit, and now what's happening? It's charging and discharging continually. So if we simply ignore the initial inrush value that we saw when we first connected it to AC, because it's a product of the simulation, we find that there is this value of current that flows back and forth from the capacitor that is limited by the capacitor itself. There's no resistor in there. So how is that taking place? And to answer that, what we have to do is go back to our calculation page and look at a calculation that will allow us to work out these values. There's obviously something opposing the flow of current in this AC circuit. So let's head back to our calculation page, and let's take a look at what we have. So capacitors, calculating caps. Let's see, for a capacitor, what do we have? Well, capacitors, we've got, look like this. And we know that capacitance is represented with a C. Capacitors are going to be measured in farads, and that is represented with an F, right? In an AC circuit, the capacitor will react to the alternation of current continually in a form that's known as capacitive reactance. Capacitive reactance, and the symbol that we're going to use to represent that is XC. So this is the symbol in equation. Got a lot of equations. Here comes another one. Well, how are we going to actually measure? How are we going to measure the capacitive reactance of our circuit? Well, the capacitive reactance of our circuit is going to be measured the same way as it was in an inductor. It's measured in ohms. So that means if we can measure it in ohms, there must be a way to calculate it. And that calculation is here. XC is equal to 1 over 2 pi FC. So what does each one of these represent? Well, 2 is a standard constant value. Pi, that's 3.14. F, that stands for the frequency, and that's going to be measured in hertz. And C, well, we already know C. C is the capacitance. And we know the capacitance is going to be measured in farads. So how are we going to then utilize this in a circuit? Well, let's take a look. First example we're going to have here is going to be of a, let's say, 600 microfarad capacitor, 120 volt AC, 60 hertz. And so it looks like this. There's our AC source, there's our cap, nothing else in the circuit. We know that that's okay. It should limit the current, and let's calculate what that value would be. So XC is equal to 1 over 2 pi FC. And remember, whenever we put values into a calculation with a formula, they need to be in their base form. And what that means is there can't be any SI prefix. This is an SI prefix. System International, that's a French way of saying metric, equivalency, a little script of U is micro, and so we have to convert this microfarad to farad. So microfarad being converted to farad, that would be the following equation: 2 times pi times 60 times, well, this into farads would be equivalent to 0.1236, right? 1, 2, 3, 4, 5, 6. We got to move it 6 decimal places. So when we pop that into our calculator, remember, all of this has to be done, right? So put some brackets in there. I'm going to do 1 divided by, open bracket, 2 times pi. So there's pi times 60 times 0.0006. Close bracket equals, I get 4.42. 4.42 what? That is ohms. Ohms of what? Capacitive reactance. So much the same as we did with our inductive reactance, remember, we have this formula that we learned in level 1. It's this one here. I is equal to E over ohm. It's not resistor's law, it's Ohm's law. And because it's Ohm's law, we can use ohms of any type in order to evaluate and calculate the value of current which resides in the circuit. So I is equal to E over, instead of doing the ohm symbol, we could represent it specifically if we wished, XC, which is then equal to 120 divided by 4.42. 120 divided by 4.42 gives me a current value of 27.14 amps. And that would be the current that's flowing in this circuit right now. Now, of course, it'd be going back and forth, but we get the idea, 27.14 amps. Okay, well, what would happen with this capacitor then if we were to adjust the frequency? Remember, 600 microfarads, the farads is a physical property and it can only be adjusted or changed by the distance between the plates, the area of the plates, or the dielectric between the plates, right? 3 different variables there. What will happen if I adjust this circuit with the same capacitor in there, but this time all we're going to do is we're going to change the frequency. So let's do the same thing. 2, we've got a 600 microfarad capacitor, 120 volt AC, and the frequency is going to be varied. I've got my AC source. There's my cap, my AC source. There's my cap. And the only difference between them is this one here is going to be 30 hertz, and this is going to be 120 hertz. What can I calculate that's common, that has a common calculation? Is this. XC is equal to 1 over 2 pi FC. So first, let's do the 30 hertz. XC is equal to 1 over 2 pi FC, which means when we do our calculation, 1 over 2 times pi times 30 times, what do we use for our calculated value of the farads? That was 0.0006. Remember, brackets equal to, so 1 divided by 2 times pi times 30 times 0.0006, close bracket, equals, I get 8.84 amps, or 8.84 ohms rather. If I wanted to calculate what the value of current was in this circuit, I could use Ohm's law. I is equal to 120 divided by 8.84. 120 divided by 8.84 gives me 13.57 amps. Well, how is changing the frequency going to adjust this? Well, let's do the calculation again. XC for this one is equal to 1 over bracket 2 times pi times 120 hertz times 0.0006 close bracket, giving me a value of capacitive reactance of 2.21 ohms. The current value that I would then see within the circuit is 120 volts divided by 2.21 ohms. So 120 divided by 2.21 gives me 54.29 amps. So what's going to happen with a capacitor when I increase the frequency? I increase the frequency, I decrease the ohms. If I decrease the ohms, I increase the current. To sort of sum it up, we could say in an AC circuit, an inductor versus a capacitor. In an AC circuit, what we would have is if we increased the hertz, that would lead to an increase in the XL of the inductor, and that would lead to a decrease in the total current that would flow in the circuit, right? Because XL goes up, that's more ohms. If you were to decrease the hertz, that would lead to a decrease in XL and an increase in the total current. When we deal with a capacitor, increasing the hertz of the source will lead to a decrease in the XC. If the XC goes down, that's the ohms, that means the current must go up. And finally, if the hertz was to be lowered, that means the XC would go up and the total current would drop. That brings us to the end of our presentation on calculating capacitance in AC circuits.